Hello, we're back with another further maths video, and today we're calculating the volumes of 3D shapes, but because it's further maths, we're going to do that using vectors. And to do this, we're going to make use of something called the scalar triple product, which is where you do the cross product of two vectors, and then you do the dot product of that result with a third vector. Now, interestingly, with the scalar triple product, you can change the order in which these three vectors have been written within this structure in certain ways that will end up meaning you still get the same result. For instance, if I choose to do the dot product of B with the result of the cross product of C and A, that particular way around, then that will get you the same result. And interestingly, if you do C dot with the cross product of A and B, that will also get the same result. Some of you might have spotted the pattern that I'm using here in order to keep the scalar triple product result being the same, because all I'm doing is making sure that the vector B is always after a vector A, the vector C is always after a vector B, and a vector A is always appearing after a vector C, so on and so forth. And all of these results you can see here follow this sort of pattern. For instance, the one on the end here is the situation where we've started with a C and then finished with a B by doing C dot product with A cross product B. So that's how we're maintaining the result. And that's important to note, because if you do just swap a pair of these letters around rather than all three in this particular way, then you do end up with a slightly different result by a factor of -1 to be precise, which does make sense because of what we already know with what happens if you do swap letters around, or vectors I should say, when doing the cross product anyway. It's worth noting though that this isn't something you have to pay particular attention to for what we're doing today, for reasons you will see later on in the video. But how do you calculate the scalar triple product? Well, one way is using a formula that's given in the form booklet, which is you basically calculate the determinant of a 3x3 matrix, where the top row of the matrix is your first vector, vector A let's call it, the second row of the matrix is the vector B, and the third row of the matrix is the vector C. But alternatively, instead of having to look this up in the form book every time, even though I guess you could also just remember it because it's quite a logical pattern, some people, me included, often prefer to just do kind of what the notation is telling you to do, which is just to do the cross product of the vectors B and C first, and then do the result of that dot producted with the vector A, because then you're just doing exactly what it's telling you to do, exactly what you're reading, if you will. But how do we actually use the scalar triple product to find the volume of 3D shapes? Well, if for instance you're trying to find the volume of a tetrahedron, and by the way, in case you don't know what a tetrahedron is, it's basically just a triangular base pyramid. But if you're trying to find the volume of one of these things, it's just equal to 1/6 lots of the modulus of the scalar triple product of the vectors A, B, and C, where the vectors A, B, and C are representing the edges of your tetrahedron. But just like in the video where we were covering how to find the area of 2D shapes using the cross product, it's a good idea to have all three edges coming out of the same vertex. Not because that is the only combination of edges you can choose with this calculation that will lead to the correct answer, but just because there are one or two combinations that won't lead to a correct answer and you want to avoid those. So just doing it this way is a safe way to just guarantee in a nice easy visual way that you have chosen edges that will definitely always work. So you could, for instance, choose this vertex over here, and then that means you would end up labeling these following three edges A, B, and C, as you can now see. Something else to bear in mind though is this formula is sadly not in the form booklet. You need to remember it off by heart. You don't need to understand where this formula comes from. I'm sure I'll have a video in my Prove It extension series at some point proving why this formula is what it is, but you just need to know it off by heart so that you can use it to calculate the volumes as and when is necessary. And let's take a look at an example so we can have a look at that in action. So we've been given a tetrahedron, we've been given the coordinates of all the vertices on the tetrahedron, and we now need to calculate the volume. So I can start by picking any vertex I like. I'm going to choose this one over here, and therefore we know we need to find the vectors representing these three edges that I've represented here. So to do that, I'm going to start by working some of those out up here to the right. So therefore I'm going to do 3 minus 7 minus 6 subtract minus 6, 0, minus 5, because that's working out this bottom one here. And so therefore, if we work that out, we'll get 9 minus 7 minus 1. And then we could work out the one over here, and that would be 8, 1, 2, minus 6, 0, minus 5. And so therefore that would get us 14, 1, 7. And then lastly, we've got this edge here, which would be calculated by doing minus 3, minus 5, 5. Take away minus 6, 0, minus 5 again. Very nice. So if we work out that, we'll get positive 3, we'll get minus 5, and then we will get 10. Okay. And so now we need to do the scalar triple product with these three vectors. So we could go ahead and do that. I'm going to do the cross product part of the scalar triple product first of all. So we'll do 9 minus 7 minus 1, cross product with 14, 1, 7. Why am I picking those two particular vectors to do the cross product with? Well, not any particular reason, and actually I should mention now that it doesn't really matter, because as I said, there are several different orders that you can do the scalar triple product in that will lead to the same result, and although there are some that will lead to a different result, it'll just be by a factor of minus 1, but that's irrelevant because of the modulus sign that appears in this volume formula. So there we go. So if we do that, we'll have minus 49 minus 1. And then we will have minus 1 lots of 63 minus 14. And then lastly, we will have 9 minus 7 times by 14, which is minus 98. Cool. And that will come to, as a cross product, minus 48, minus 77, and positive 107. So there you go. And so therefore, if we want to work out the volume of this pyramid, the volume will equal 1/6 lots of the modulus of the third edge vector we hadn't used yet. So that's 3 minus 5, 10. Dotted with our cross product that we just did, which was, of course, 9 minus 7 minus 1 cross product with 14, 1, 7. So therefore, this calculation is what we need to do. We've already done part of it, so therefore it's 1/6 lots of the magnitude or modulus of 3 minus 5, 10, dotted with minus 48, minus 77, 107. And therefore, then we can work that out, because that will just be 1/6 lots of the modulus of 3 times by minus 48, which is just minus 144. We have minus 5 times by minus 77, which will be a positive 385. And then lastly, we've got 10 times by 107, which is, of course, going to be 1070. That comes to 1311, and because it's a positive number, the modulus does nothing to it, so therefore we're just doing 1311 divided by 6, which comes to 437 divided by 2. So that is the final answer. The volume is 437 divided by 2. Just to quickly illustrate though, what happens if you'd done the scalar triple product using the other method? What would that have looked like instead? Well, all you would have done to do the 3 minus 5, 10 dotted with 9 minus 7 minus 1 cross product with 14, 1, 7 is just do the determinant of 3 minus 5, 10, 9 minus 7 minus 1, 14, 1, 7. If you do that, it comes to that same number of 1311. So that's an alternative way of doing this stuff if you prefer. But it's not only tetrahedrons that we can work out the volume for using the scalar triple product. We can also work out the volume of parallelepipeds. Yes, you heard me right. That's parallel, the letter E, and then the word piped. And a parallelepiped looks like this. I've also heard some people pronounce it as parallelepiped, but either way, basically what a parallelepiped is it's basically a cuboid where the angles don't have to be right angles. So therefore that means the faces don't have to be rectangles anymore. You can have parallelograms on any of the faces instead. So how do you work out the volume of a parallelepiped? Well, it's just even more simple than a tetrahedron. It's basically the formula for volume of a tetrahedron, but with the sixth missing out the front. So if anything, it's even easier than a tetrahedron. So really, that's all there is to it. It's just that formula. Just like before, unfortunately, this formula is not in the form booklet, so you need to remember off by heart. Good news is, though, because it's so similar to the tetrahedron one, you just need to effectively remember one of the formulas. I often remember the tetrahedron one, and then just remember the parallelepiped doesn't have the 1/6 in front of it. And then also the vectors A, B, and C are again therefore representing edges of the shape. Again, you want your three edges to be coming out of one particular vertex. It doesn't matter which vertex that is, which is pretty neat and convenient, but you do need to choose a particular vertex, whichever one you want to choose, and then have your three edge vectors all coming out of that one corner, like so. But ultimately, because it's just a formula, I'm not going to do another basic example. I'm just plugging stuff into the formula and that's it. So let's do a second example where we are actually having to work backwards to find a missing value. But we still therefore will be making use of that formula. In this particular question, we've been given the volume of the shape is 20, and then we've also been given vectors for 3 of the edges of the parallelepiped. They're currently not all coming out of the same vertex, which might appear to be a problem, but conveniently, if I pick this corner here, I notice that 2 of the vector edges are already coming out of that corner, so that's a good start. And then although the third one isn't, because it's a parallelepiped, this edge and this edge must be the same vector as each other. So in reality, we do have 3 edges all coming out of the same vertex, so we have everything we need to do the formula. So therefore, we know we have enough information to get started. Something worth bearing in mind with the formula for this one, because we've got an unknown h in there, some people might prefer to do this by doing the cross product, then scalar product method, rather than doing it all in one big go using a 3x3 matrix, just because doing the determinant with a 3x3 is a bit annoying when you've got an algebra letter in there. So if you're very tactical with this stuff, what you can do is make the one that's got the algebra letter in the one you're going to just have to dot product at the end, because doing dot product is really quick and easy. And then therefore make the ones that have numbers be the 2 that you do the cross product with. So I'm going to do the 1, 3, minus 6 cross product with the 4, 6, minus 8. And of course, we know that needs to be modulus, if that's a verb. I've just made it one if it's not. And therefore, that's equal to 20. So this is basically the equation that we need to solve in order to find h. Starting off by working out the cross product, we can do 1, 3, minus 6, cross product with 4, 6, minus 8. And therefore, that is ijk, technically underlined, 1, 3, minus 6, 4, 6, minus 8. We've just got to calculate that as a determinant. And if you do that, you'll get 12, minus 16, and minus 6. Nice. This is just a vector at this stage. So therefore, we can now do 7, 8h dotted with 12, minus 16, minus 6. And therefore that's still equal to 20. Working that out, 7 times by 12 is, of course, 84. We've got minus 16 times by 8, which is minus 128. And then lastly, we've got minus 6h. But this is being modulus. And the reason that's important is because it means we now have to watch out. Okay, we could simplify the minus 128 and minus 6h. And if we do that, we'll end up with minus 44 minus 6h modulus equals 20. But the thing to bear in mind is that this now effectively splits up into 2 separate mini equations to solve, because we either have that minus 44 minus 6h must equal positive 20, or we have that minus 44 minus 6h must equal negative 20, because that's what happens when we undo the modulus sign that's there. And therefore we've got to solve those 2 things individually. So therefore we get 6h equals minus 64. So therefore h is equal to minus 32 over 3 is the first option. Or alternatively, we could end up solving it with the other one, and that would get us 6h on the right hand side. On the left hand side we get minus 24. So alternatively, h could equal minus 4. So there we go, those are our two answers. So that's just us using the formula for calculating the volume of a parallelepiped. It really is as simple as that, just using a formula and doing what you need to do in order to carry that formula out. But I do want to finish off with a few extra details. For instance, what happens if you need to calculate the volume of a shape that isn't just a tetrahedron or just a parallelepiped? For instance, this shape here, which is a pyramid, but it's not a tetrahedron because it's got a quadrilateral at its base, whereas a tetrahedron requires a triangle at its base. So if this happens to you, then chances are in further maths, it's just a shape made up of a combination of tetrahedrons and parallelepipeds. So that is the case here as well, because you might notice that we can just take the quadrilateral at the bottom and split it in half along one of its diagonals. Because if you do that, you'll then end up with two triangles, leading to, therefore, two tetrahedrons. So, therefore, that's quite neat. Something to be aware of, though, is if the base had been conveniently a parallelogram or a square or a rectangle for our pyramid, then technically that means the two halves of the quadrilateral would be the same as each other due to the symmetry of those shapes I just mentioned, and therefore the two tetrahedrons you split it up into are the same as each other. So it's worth mentioning technically in that case you could just work out one of the tetrahedrons and then double it, and therefore that would have the effect of us just using the formula 1/3 lots of the modulus of the scalar triple product, which is interesting because that links back to the formula for a square base pyramid, which is 1/3 times the height times the area of the base. But because many of you probably don't want to have to remember an extra formula for something that's super rare and only occasionally, very rarely comes up, therefore instead you might want to still calculate the volume as two separate tetrahedrons and add them together. That is the case here as well, because the two tetrahedrons aren't going to be the same size, because the two halves of our quadrilateral aren't the same size, because you might be able to see that our quadrilateral is a trapezium. But therefore, that sounds like a bit of a chore, having to work out two separate tetrahedrons and do two separate scalar triple products. However, you can be tactical to reduce the amount of work you actually need to do in order to do those calculations. Because you notice if we're splitting it up using that diagonal at the bottom, there's two edges that could be used in both tetrahedrons. This edge here along the bottom and this edge here could be bordering both the left hand and right hand tetrahedrons. And the reason that's useful is if you call these the vector B and the vector C, then that's really useful because the most tedious part of doing the scalar triple product is doing the cross product part. And therefore, if you only have to calculate that once because these two edges are part of both tetrahedrons, that saves a lot of time. Because then the first tetrahedron can just be done by doing the dot product of this vector over here, which I'm going to call A1, with that cross product, times by a sixth after modulusing it, and then add on the dot product of this vector over here, A2, let's call it, dotted with, again, that same cross product. So there we go, being sneaky and tactical to save some time, because then we're only having to do a couple of dot products, which is the easiest part of doing the scalar triple product, because it's just a bunch of multiplying and adding. So there you go. Be smart and you can work these things out, no problem. Other things to be aware of are also there's any excuse for them to bring in other areas of maths into this stuff. So do remember at GCSE there was the formula density equals mass divided by volume. They could involve something like that in one of these questions as well. So do remember that form from GCSE as well. Okay, that will do us for today's video. Hopefully you found this video useful, and I'll see you in a future video. Goodbye.